Hi, thank you for joining our webinar today. My name is Binna Seo, and I'm a senior application engineer at Bentley Systems. I'm in charge of the user support of the software named SACS and MoDeTo. The topic of this webinar is the cost-effective design of the monopile foundation of offshore wind turbine structures. Let me start. Here are the contents we will discuss today. First of all, we'll briefly review the pros and cons of the current design methodologies of fixed-type offshore structures. As you see, there are PY method and three-dimensional finite element method and PISA method. This PISA method is our main topic today. And after the overview, I will introduce how the methodology is integrated with our software. Let me move on to the next page. The first methodology I will introduce is the PY approach. As you see in the screen, in this approach, soil and pipe foundation is represented by one oiler Bernoulli beam, supported by independent lateral springs along the pile. Local soil reactions are represented by a bunch of springs in one-dimensional plane, as you see in the screen here. This approach is developed in 1960s to mainly prevent the collapse of the fixed jacket type structures and has long been used in the offshore oil and gas industry. The main benefit of this approach is that it needs less computational effort. So the runtime, the analysis time is very short, relatively very short, and also very easy to integrate foundation with the linear elastic main structures for global structural analysis. This approach works well for slender piles, but it has some limitations or uncertainties for monopile foundations. Let's take a look at this in detail in the next page. First of all, the PY approach is based on test data of a long slender pile with a diameter around 610 millimeters. And length to the diameter ratio is 34. The stomach here indicates the slenderness ratio and load eccentricity, which API used. Slender piles were used to infer the original PY curve. But monopiles of the monopile foundation of the offshore wind turbines are not slender. The green part here indicates the region of the offshore monopiles. This geometrical difference causes many other differences, especially in soil reactions. This is due to the different failure mechanism. The pictures on the screen shows the actions of the monopile and the slender pile. As you see, monopile tends to show the rigid body motion rather than bend. By having a rigid body motion, it attracts the more soil reactions along the pile and at the base of the pile. So we need to consider the additional soil reactions, soil springs here. But these additional soil stiffness are not considered in the traditional PY approach. But it is not considered. This is the first uncertainty. And furthermore, we need to check the serviceability and fatigue limit of the structures. And as we know, here, stiffness of the foundation plays a significant role when determining dynamic characteristic of structures. However, it is in question whether this PY curve is able to provide a more realistic representation of the foundation stiffness or not, because some of the steepness, as we talked right before, some of those steepness contributions are not considered. This is the second uncertainty we can think of. The last uncertainty is the effect of the cyclic loading. In the PY method, this is considered by modifying the static PY curve with appropriate empirical factors to reduce the steepness and strength of the soil. This is a very pragmatic way, but gradual changes of the foundation steepness is not considered in this method. Especially, PY method does not take account the magnitude of the cyclic loads, or number of cycles, or accumulation of damages. The MVGL requirement specification suggests to validate those effects using finite element analysis, but does not specify the detailed method there. The other way is to use the three-dimensional finite element method. As we know, this gives us a good understanding and very detailed understanding of pile-soil interaction. I mean, measuring the whole volume of the soil and solving the system gives us the most reliable result. However, we need to carry out each analysis for one loss and for one geometry and one soil property. What I mean is that the analysis results are for one load case and one geometry and soil. As we know, usually we need to analyze the hundreds of cases. So I'm pretty sure it will take days or weeks to get complete set of final result. In short, this approach is not practical. This only can be used for validation purpose or local analysis for a specific or problematic case. The PISA method is an alternative of the PY method and 3D FE analysis. This method is developed from the PISA project to improve the efficiency of laterally loaded monopiles. This is a key of the future generation offshore wind farms. The method simplifies the foundation system to one-dimensional system like PY method does, but it uses soil reactions calibrated from three-dimensional finite element analysis. Furthermore, it considers the additional soil reactions caused by rigid motion of the modopile. What I mean is, the picture here on the right-hand side shows the failure mode of the slender pile under the lateral loading at the pile head. The soil reaction in this case would be the horizontal reaction and the skin friction at one side of the pile. However, as we talked in the previous slide, monopiles are not slender. This results in additional soil reactions along the pile, both face of the pile and also at the base. We'll come back to this topic soon. Anyway, this PISA method considers the true soil reactions supporting monopiles. Because this approach uses the one-dimensional approach, it is very fast. The analysis time is very short, relatively, and easy to integrate with linear structure above the mud line. At the end, by considering the additional soil resistance calibrated by 3D FE analysis, the length of the monopiles can be reduced up to 35%. Our software PLAXIS, which will be introduced later part of this presentation, joined this PISA project, and PLAXIS MoDeTo is developed based on this approach. This PLAXIS MoDeTo is the first commercial software to accept this PISA approach. The plot here shows the deflection of a slender pile and large diameter piles along the pile in the soil. As you see, it matches to the behavior of the 3D FE analysis we saw in the previous slide. This plot is generated by the monopile design module of PLAXIS named PLAXIS MoDeTo. Let's take a look at more details about the PISA method. As you see, the traditional PY method uses the slender pile, and this pile is assumed, represented as a Euler-Bernoulli beam, which does not consider the shear effect. But in the PISA method, the beam is represented by a Timoshenko beam, which considers the lateral beam displacement, which occurs due to the shear strain as well as lateral displacement due to the bending. This is to ensure that shear deformations are properly considered. And as for the soil reaction curve, both approach uses the Winkler approach. In other words, the beam is supported by nonlinear springs. But in the PY method, it only considers the lateral springs, lateral reactions. However, in the PISA method, as we talked before, the additional soil reactions are accounted for. They are, as you see here, they are distributed moment along the pile, and the moment and the shear at the base. This is due to the different failure mechanism. And furthermore, instead of a curve over a certain geometry and type of soil, PISA methods parameterize them into a calibration space, where we can modify the geometry and the rows and the strata. All of these things here are incorporated into PLAXIS MoDeTo. Now let me introduce our software, which enables you to follow the PISA method and more. First of all, as regards the PLAXIS, it was initially developed in TU Delft as an application of the computational modeling to the Dutch fluid defenses. And later it was switched to an independent software company. It is used in almost every application of geotechnical engineering, from offshore foundations to tunnels, dams, and urban constructions. PLAXIS joined forces with Oxford University and Fugro to develop PLAXIS MoDeTo, which is the PLAXIS monopile designer. This PLAXIS MoDeTo incorporates the PISA method. SACS was founded in the early 1970s out of software developed for NASA's Saturn rocket program. The original writers saw a need for space frame structural analysis solutions in the offshore industry, and then SACS was born. SACS has various sub-modules supporting linear static or dynamic analysis, nonlinear plastic analysis, transportation analysis, etc. It also has a feature to do the pile structure interaction analysis and single pile analysis named Pile 3D, based on the input soil property. For the analysis of monopile structures, we recently developed an interoperability of these softwares. The idea is to calculate the soil reaction curves in the PLAXIS using the PISA method, and PLAXIS output the soil input files for the analysis in SACS, and then the other subsequent analysis, like a structural analysis with a linear structure, is proceeded with SACS. The workflow here is the workflow to analyze the monopile structure. The source of the image is at the bottom. Once we are done with the site investigation, PLAXIS take a part of 3D FEA analysis and parameterization part. Then export all these soil reactions in format of SACS. Then, with the file from PLAXIS MoDeTo, SACS runs the FEA analysis of a pile or piles using the pile 3D module. And in the picture, pile had a super element which represents the stiffness of the linear structure will be available for more rigorous analysis. And also SACS has a PSI module which represents the pile structure interaction analysis. This module allows us to analyze the nonlinear foundation and linear structure at a time through the iteration. Let's take a look at this more. What SACS PSI and Pi3D module does is, as you see in the picture here, the foundation is represented by a beam, and the modules discretize the beams and attach the springs along the pile. The type of the springs are axial and end-bearing, and lateral and torsional springs, as well as the shear and moment springs at the base, and distributed moment springs along the piles. As we talked before, these are from the PLAXIS MoDeTo using the Pisa method. As regards the functionality of the Pi3D, it analyzes the pile axial capacity versus the pile length and simulate the depth loading of a single pile or collection of the piles, but without linear structure above. It uses the finite element method, and the piles are represented as a Timoshenko beam. This is in line with the Pisa method. This finite element method, the Pi3D use, allow us to consider the localized large deflections of a pile. This characteristic of a Pi3D module matches to the Pisa method. So this Pi3D module will be enhanced in the future to fit more with PLAXIS and Pisa method. As I talked in the previous slides, for now, we are limited to a single pile analysis without linear above structure. Our future enhancement will be add a stiffness of linear structure to the pile head joint. And furthermore, perform the analysis together with hull structure with soil properties from PLAXIS MoDeTo at the end. This is all I prepared today. If you have any questions or want to know more, please send us an email. I can give you a live demonstration to show you how it works. Thank you again.